Thank you so much for joining our session today. The NEOSEC Ocean Literacy Summits connect scientists and educators based on the premise that science and education both inform research and practice. So working and learning together really improves all of our work. So I know Konrad and I are both really excited to be part of this. Just a few Zoom instructions and housekeeping before we get started. The sessions are being recorded and will be available for later viewing. So you might want to go back and look at some concurrent sessions that are happening at the same time. Also, that may inform your decision whether you want to share your camera or not. So please do whatever you're most comfortable with. If you are unable to share your camera or unmute yourself and you desire to do that, please just send a message to Kimberly. She's our tech support today and she will sort that out for you. You are all muted at this point. Please stay muted until the discussion portion, so until Konrad's talk is over. And then at that point, we'll invite you. You can either ask your questions through the chat box or you can unmute yourself and we can have a nice discussion. We do invite you to participate through the chat feature, submit your questions. I would say while Konrad's talking and they come to your mind, and then we'll try to address them when he's all done. So you should be able to access those features from the bottom of your screen, the little chat selection. So just to introduce us, so I'm the moderator today. My name is Grace Simpkins. I am the Woods Hole Sea Grant Marine Education Specialist at the Woods Hole Oceanographic Institution. I've been with Sea Grant for about 3.5 years, but I've been doing marine outreach education for much longer. I do teacher professional development workshops. I go into classrooms and try to spread marine science wherever I can. And today it's really my pleasure to be introducing you to Dr. Konrad Hughen. He's a senior scientist in my department. So we in the marine chemistry and geochemistry department at the Woods Hole Oceanographic Institution here in Woods Hole, Massachusetts on Cape Cod. His research generally seeks to reconstruct past changes in climatic and environmental conditions in order to understand the mechanisms of abrupt climate shifts and their impacts on terrestrial and marine ecosystems. Now, I didn't want to read his whole bio because I figured you could do that yourselves. I really want to get to what Konrad has to share with us. Really excited about everything he's done. We've done some teacher workshops featuring his material in the past. So that's my intro for you, Konrad. I would love to hand it over to you.
All right. Well, thank you, Grace. That's enough introduction. I'm just going to go straight ahead and start to share my screen. And the little tiny bit of sound that might come. Oh, come on. All right, can everybody see this?
Yes.
Can anybody see this?
Yes.
Yes, it's just not in presenter mode yet.
Grace, can you see this?
Perfect. Now it's in presenter mode. You're all set.
Sorry, everybody was muted on my end, but yes, is this good?
Yes, you see it. It looks great.
Thank you. Sorry, I had my own muting on.
Okay.
Yeah, so thanks for that introduction, Grace. I appreciate it. Basically, I just want to get right into it. The idea of what I do, the reason why I do what I do is really based about trying to understand if we're anticipating future climate change, we really need to understand what the natural climate variability is. And in particular, I talk about long-term natural climate variability. We need to know what multi-decadal to century scale climate changes are to be able to recognize them, but the instrumental record is just too short. We have about less than 50 years of satellite records and then 100 years plus of records from different parts of the planet, but very spatially sparse in some places. So we really don't have enough to understand the global climate system on these long scales. So we need proxy records. And in particular, we need to extend the observations in time, obviously, but as I just mentioned, also in space. So sometimes we're not necessarily building these proxy records back in time, but we're trying to fill in space where we don't have good observations, even though we might have them somewhere else. And today I'm going to talk about corals and specifically the geochemistry of coral skeleton. The chemistry, the indicators in the skeleton there are many different things to analyze, and they reflect many different climate variables. And I'll talk about some of those today, and also how they can be used to track large-scale climate systems like the South Asian monsoon. So really the whole basis for all of this work is just that massive coral colonies, really big corals can grow and live for centuries. And so these are the kinds of corals that we target. We look for these, we engage the locals and find out where these exist. And start these underwater drilling operations. We do this with scuba and a hydraulic drill that runs off of a boat. And the drill itself is a hollow tube, a hollow drill bit with a diamond tip. So it leaves behind a solid core. And we take these one drill bit at a time. You can see the living part of the coral is only that very thin skin, and all the rest underneath is rock. And so we're drilling down through that rock. Obviously, the way that this works, the drill head comes off. It's operated by seawater, so we're not bringing any oil or hydraulic fluids out onto the reef. And bringing up the drill bit, Justin's telling me we have a core inside, and you'll see that sometimes these pieces come out in a solid core. A particularly nice one here. And then we would put on an extension rod and continue the process. And you can see the cores that we've already taken laying there. And when we're done with this work, we sweep off the coral, we put a cement plug in the hole, and these corals will recover from our footprints within days. And certainly the hole that we've drilled through will be grown back over and covered within a year or two. So as long as this doesn't happen every year, these corals recover just fine. They do well. And the reason that we're targeting these corals really is summed up in this slide. Corals, like trees, grow with annual density bands, rings, effectively. And so these allow us, they provide really strong dating control. They allow us to build chronologies. And the resolution, we can drill tiny powder samples and do this chemical analysis at sub-millimeter scale. So we develop easily monthly resolution records that go back for centuries. And because these are at fixed locations, we can compare sites between sites and actually reconstruct larger scale systems. And so here's another example of an X-ray of a coral drill core. You can see the density bands in the middle, and we can reconstruct things like temperature and salinity, or river runoff, and even windborne dust. We can reconstruct changes in anthropogenic pollution. And even lately, we're looking at organic biomarker signatures of coral health still contained within the sediment. So there's a wealth of information that we can extract from these cores. And I want to give a couple of examples. So one case study is looking in the Red Sea and looking at strontium to calcium ratios in the skeletons and how that reflects sea surface temperature. So this is an example of the strontium calcium ratios measured in the coral skeleton are in red. And I'm comparing that, and of course, this is at 1/2 millimeter resolution down the core. And we're comparing that, the blue line is satellite sea surface temperature measurements for a gridded square over the location of this coral in the central Red Sea. And so the agreement is very strong. You can see very obvious, I'll use my, let's see if I, no, I lost my pointer. That's all right. You can see that there are obviously great matches between with the seasonal cycle, high in the summer, low in the winter. But in addition to that, I want you to notice that there's also, especially look at the winter, look at the cold end here. And we can see that there are times when the winters are very cold and times when they're not as cold. And so this agreement is not only of the seasonal cycle, but it's also showing this agreement at interannual timescales, which is actually an important test. Many things can have a seasonal cycle, but if we're looking at interannual signals, then we're really pushing this to be temperature alone without other potential seasonal influences. And we can quantify that. Here's an example of strontium calcium versus SST for the warmest site in the south. You can see there's a very strong relationship, and when we quantify that with a regression, we get very, very strong statistics. Now, what I'm going to show now is that as we include additional sites from the Red Sea, going from this warmest site north, we see that the data continue to occupy the same strontium, calcium temperature space, but including colder temperatures and, in fact, higher strontium. It's an inverse relationship. And so we can see that all 6 of these cores basically inhabit the same space. They show a very similar relationship, which gives us confidence that this proxy is working well as a temperature recorder. But in addition, you'll notice, if I go back through these, that starting from the warmer south and as we go colder, we're not extending into space, we're also getting slightly steeper in slope. So this paper that came out in one of the papers that we hope to make available to you came out in 2018, describing these relationships and finding that there was a link between the slope of this relationship and the mean temperature at the site. And that's something that we actually found in globally as well. So even though there are differences in the strontium temperature relationship between corals, we believe we're understanding some of what that variability is due to, which again increases our confidence in the ability to use these corals to reconstruct temperature. So here's an example. Again, we have this is the exact same time period that I was just showing, with satellite data shown here in orange and the coral data in blue. And what I just want to show is that this is, the limit of the instrumental record is quite obvious in terms of only being 30 years or so, but the coral keeps going. And so the coral, this early relationship that we find helps anchor what would be the rest of this coral record that extends back for nearly 250 years. So the value of the corals is shown well, I think, by this slide. We have these instrumental records that are global and based on satellites, but they really just don't extend back very far. And with corals, we can effectively extend what's almost an instrumental record back for hundreds of years. So that's one case study just showing that temperature is reflected in the coral the chemistry of the coral skeleton. Sorry. And another case study is looking at different aspects of the South Asian monsoon. So these are 2 records from the central Red Sea in the north and the northernmost Red Sea below. And these data can be analyzed any which way, but one thing that we can look at is the average winter temperature between these sites. And right off the bat, we see some patterns going back in time where they show a great deal of decadal and centennial century scale variability, but they're in antiphase. When the northern site gets warm around 1830, the southern site gets cold. And they follow this antiphase pattern. And what's fascinating is that this is supported by what we know about the wind-driven circulation in the Red Sea. This is a complicated slide, but really briefly, the winds come down from the north and cool the north. The sun is strongest in the south, and the warmest waters are in the south. So when the wind blows, of course, it cools the north. But what's fascinating is that the Red Sea is kind of weird and has this reverse circulation where that cooling in the north creates a northward current. So the current flows northward against the wind because of the density. And as a result, you get warm water flowing north from the south while you get cooling in the north. And if we look at data, temperature data sorted by the differences between the strongest and the weakest wind years between 1950 and 2010, we see this pattern, which is that it cools in the north, but it not only cools in the north, it actually gets warmer in the south. So this is a very specific spatial fingerprint. And what's fascinating is it's what our 2 corals are seeing. So that gives us confidence that this record, which is the temperature gradient between the North and Central Red Sea, is actually recording wind strength. And the winds in this area, now here's the Red Sea on the left corner, and these winds are flowing down the Red Sea. Well, if we take that time series and correlate it against global sea level pressure data, this is what we get. The strongest correlation is to the Siberian high. So the Siberian, and this is winter data, so this is the winter Siberian high, also shown as the low temperature. So low temperature, high pressure. And this is basically the driving force behind the winter monsoon. So this time series is a time series of the strength of the winter South Asian monsoon going back 250 years. So that's one example of how we could use these corals, not just to record a single point, but actually to study larger scale patterns. And briefly, this is the last case study. I want to also talk about the summer monsoon. This is the Indian monsoon that most people have heard of, shown here with the large rain, occurring over eastern India and Southeast Asia, with the winds coming in from all directions. Sometimes it's thought of as just the Indian Ocean, but the summer monsoon is really more like an octopus. And we can see that over the Red Sea, there's two corals shown on the left, and on the right is a better blow up, where in the summer with these monsoon winds, we get dust storms. And these dust storms blow in and they blow all the way across the Red Sea and they impact the sites where these corals are. And what we see here, this is both barium calcium and strontium calcium. The strontium in red showing the seasonal cycle of temperature, just like we saw. But in black, the barium shows the same temperature cycle, but it also shows these spikes. And these individual spikes, each of these samples is about 2 weeks worth of data, each one of those dots. And so those dots are capturing these 3 to 4 day dust storms. So this is evidence that our barium in this coral is capturing these dust storms. And if we measure these data not monthly but annually, what I'm showing here in red and blue, the top and bottom, are the two different corals that are now showing this is that barium calcium, this barium dust signal. And this is from two different corals that were drilled, that were measured for barium. They were also measured for strontium. The strontium has the temperature signal that we corrected the barium for, and we still get this level of agreement. So the black line is just an average, but the red and blue lines are two different corals. And I know I'm getting excited here, but this is phenomenal agreement for two different coral records going back 250 years and showing the same patterns. So similarly, we can take that time series and we can regress it against global pressure. And when we do that, we find this low-level signature over the Indian subcontinent. That is the signature of the Indian monsoon. And that is what is reflected in our dust record from the Red Sea. So we have both this low pressure and then the high sea surface temperatures, and together with the pressure fields, these are the drivers of the summer monsoon. So we therefore interpret this as the summer monsoon, the strength of the winds, and we can see that there's both multi-decadal variability and century scale trends. And the same thing is true with the winter monsoon. We see multi-decadal variability, century scale trends, and these are the kinds of signals that we are seeking out and studying here. I'm not going to read these. Skeleton chemistry records climate, and we can put together records of large climate systems like the monsoons, especially with these multi-decadal and century scale signals. We can actually address problems where the monsoon is supposed to be getting stronger and rainfall says it's not, and yet the winds now say they are, which is more in agreement with models. So it's a complicated story that we need to dig into further, and that's why we do this work. And I'm going to stop there. So thank you very much. I appreciate it. And we can do questions.
You were super quick, Konrad. I didn't have to stop you at all. Yeah, came in about 15 minutes. So I encourage anyone who has any questions. I'm keeping an eye on the chat, but you're also welcome to
I'm desperately here we go.
Yeah, to unmute yourself. I know that one of the things Konrad and I, just to sort of chat a bit while we wait for some questions to come about, one of the things that Konrad and I talked about when thinking about, how might this be something you could use in your classroom or any programming, was if you're working with your students on linear regressions, or looking at correlations, some of these data sets might be nice to do that. But I don't want to get ahead of ourselves because I want to hear from you all. Any questions you have or ways that you think you might be able to use these concepts in the education setting that you work in.
Also, please let me know if you are unable to unmute and turn on your camera, and I can go ahead and do that. So you can write in the chat box.
Yeah, we could definitely take things in chat.
And the paper that Konrad referenced, I put this in the chat, but the paper that has the information in the data set is linked to this on the app. So with that resource is linked, as well as another one.
Hello,
Yeah,
this is Valerie. I have a question. Is that okay to go?
Yes,
Of
of
course.
course, Valerie, go ahead.
Hi, Konrad. I'm interested in your work, and I'm just wondering what your new projects are and what you want to be going out and doing next.
That's a great question. There are a couple of different, I kind of wear, well, we all wear hundreds of hats, but I've got two big ones that I wear with these coral records. And so in the inorganic, going after climate, there's a couple of things. You can see that I'm focused on the South Asian monsoon. And that's really one big part of this, is that we're kind of trying to close in on the South Asian monsoon with records from the Red Sea, from Sri Lanka, from the Indian Ocean itself, and trying to constrain. I called it an octopus, but there's all these different arms that basically feed the monsoon, and it's not just a simple Indian Ocean, Asian subcontinent system. It's more complicated than that, and so really trying to characterize that as one thing. So I've been doing a lot of work in Sri Lanka and trying to get more long records that we can do this work on. And then there's a second, I was mentioning really briefly just that we're looking at organics. There's not just that corals record climate, but corals are also, honestly, canaries in a coal mine, very sensitive indicators of climate change themselves. They're balanced symbiotic systems, so any changes in climate really affect corals, and that's why bleaching is such a common problem these days. So one of the things that we're trying to do and having some success in, so this is really exciting, is getting organic compounds out of the coral skeleton. And these are organics left over by the living coral host and their symbionts. They have photosynthetic symbionts inside their tissues, and they do leave behind molecular evidence of themselves. And some of those molecules they leave behind are indicators. They can be used as indicators of whether or not the corals were undergoing stress during their life. So we're trying to reconstruct past stress events like paleo bleaching, and it's working. So that's really exciting. We don't have long records yet, but we're at the place where we know which indicators to look for in the skeletons, and we have sensitive enough equipment to pull those things out. So that's pretty neat. I like that. That's fun.
Along those lines, Konrad, I've just been working with Arctic information, and my students were able to map out or graph the changes in temperature along with the reduction in sea ice in the Arctic, and they see this nice correlation from that. Is there data in your data sets that might be able to be used like that with students, where they would be able to compare them and see an inverse relationship or a correlation? Just thinking of how to use something in the classroom.
Yeah. So I think that those kinds of correlations aren't, even though we're looking at very different parts of the planet, it's not crazy. We know, for example, so one of the things that temperatures are going to be having impacts in many places. And so you would see very strong Arctic trends in temperature. They would correlate with sea ice, and they would also correlate with temperature records from corals from maybe Bermuda or from higher latitude locations. When you get into the tropics, trying to compare gets a little trickier, just because the global system, when you get in the tropics, it's not really about temperature anymore. It's so much more about the hydrology and wet season, dry season, or trends in that. So on the one hand, straight up comparisons could be complicated by the fact that these are dynamic climate swirling masses. It's a very complicated system. But one of the things worth looking into, if you were looking at sea ice and temperature, there's other things that have been recorded, especially during the instrumental era, that I'm referring to here. All of these, I call them large scale climate system. We also call them the oscillations, the O's. There's the Arctic oscillation, the North Atlantic oscillation. These are spatial climate systems. The Arctic oscillation is how strong the polar vortex is, and it can be strong and tight, or it can be weaker and looser, and that has it has a spatial pattern, and it has temporal. It has a known record of variability over the past 150 years, where with periodicities, it has a 15-year beat to it. And the North Atlantic oscillation, which is kind of the Atlantic arm of that Arctic oscillation, but it's a little bit different because it has driving from low latitudes as well. You know, it has a specific signature beat, a 13-year beat, and also multi-decadal variability. So when you're looking at Arctic systems and trying to compare those to the El Nino Southern Oscillation, the big O, it's usually not as simple as just looking at, say, temperature in one spot and temperature in another. Sometimes you have to start looking into these larger systems and then trying to see if there's interaction between those systems. I don't know if that actually helps. It's kind of babbling, but
Konrad, I was just kind of looking for a coral reef kind of similar situation as the Arctic. Not to continue working in the Arctic, but to look at coral reefs and some other data to make connections, if you know what I mean. So it's just
absolutely.
food for thought. We did look at the polar vortex too when we did our work, but I'm trying to transfer the same type of activity to coral reefs and so on. So it's maybe food for thought. I just want
I think one thing that can be done that's kind of neat that way would be looking at coral records and comparing them, for example, if they're in the Pacific, comparing those to these climate indices like to ENSO, to El Nino Southern Oscillation, because that's kind of cool. You can start to see how ENSO has a specific spatial pattern, and you can look at corals inside that pattern and see that, okay, the corals on this side are correlated to the ENSO pattern, and the corals on the other side are anti-correlated. There'll be positive and negative correlations based on positive and negative nodes, and that's kind of those are fun, and that's stuff that you could do.
And Konrad, I think the question too is like, where would they access the data set? And I know you and I talked about this. Are there data sets out there that you could direct them to? Maybe we can put them in the chat box, or we can add them as a resource after that they might be able to use in their classroom.
Yeah, a really good resource. NOAA. So NOAA has the Climate Data Center, but there's a paleoclimate data. They have a data center. They have many data centers, but they have both climate data that are like what I'm talking about. They have indices of El Nino, North Atlantic Oscillation. A lot of these climate systems have different indices that have been put together based on the data. There's different ways of doing it, so there's different records. And all of those are collated and collected and actually archived very well with information explaining what they are, what drives them as best as that's known. And so that's the NOAA Climate Data Center, the CDC. And within that, there's also the Paleoclimate Data Center. So you can access both. You have to look around a little bit. You can access all of these modern day indices and indicators of the way that we think the climate works over the past couple of centuries, but then you can also access paleoclimate data from the past several decades. And that's everything from ice cores to corals to tree rings to sediments. You can search by corals, you can search by location, you can search by scientists, you can search by a person or a place or a thing. And so like my data are in there as well. But as Grace pointed out, we were talking about this yesterday, most scientists like myself will put our data in. The coral data are in there, and you can go get them. But the satellite data is not. We usually don't archive the satellite data, which are already archived. So to put together comparing the coral to the climate, you like seeking out the climate data is still needs to be done. That wouldn't just be available ready-made. Like, here's all the temperature data that go with these corals. That usually isn't the way it works.
And I just put a link in the chat box just because I want to move on to a few other questions, but I did put a link in the chat box to that NOAA Center for Environmental Information, and you can go, like Konrad said, and do a search, but there's there's a lot of data online. So if you're interested in looking at some of Konrad's data or some coral data, you can find it there.
So Ewan Scott asked a question. Can I read this out and respond to that in the
Yeah,
chat?
I was just going to ask the first one first, if you don't
Yes.
mind. And that's, are you using these cores to look into the impacts of climate change with regards to acidification and warming and et cetera? And then we'll follow up with the other one.
Yeah, yeah. No, that's a great question, because I think that these corals record so many different aspects of climate that the answer is yes. We're looking at impacts of, we're looking at changes in temperature. There's two ways of looking at this. One was, it's really like, what are the impacts on the corals? So that's a really, so there you go. And of course there is bleaching, temperature driven bleaching, but there are other changes that occur, and some of those depend, people sometimes try and use them as proxies themselves. So corals, their growth rates are affected by their health status. Are they stressed or not? And so growth rates can drop if temperatures get too high. But so that is an impact, and people have published quite a bit on that. But it's also something that's a little bit of a, many things affect growth rate. So it can be a very strong indicator of change, but it might be difficult to back out exactly what caused those changes in growth rate at any given location. There's other things as well. We find, so interestingly, things that aren't always visible. So bleaching, very visible, clearly a traumatic, if it continues, the coral dies. If it recovered, if the conditions improve, then the bleaching stops and the coral lives. And growth rates can slow down or even stop, but then they can recover again and the coral can continue growing. Some of these organic chemical changes we're looking at are really based on the physiology of the cells. So we're learning with culture studies, how do symbionts in tubes, just single-celled algae symbionts, how do they respond to temperature, but also to acidification and to chemical exposure and to disease? And we can see changes in how the symbionts are making their lipid membranes, their actual cellular structures. And so we see those changes, and those are some of the things we're looking at in the coral skeletons as well. It's not quite something like, oh, how is, like, what's the coral's big visible response? It's usually a very hidden response. It's a molecular, it's a cellular level response, but these are things that we see. And even the molecules that they're putting out, not just what they make of their own bodies, but corals are always exchanging nutrients with the waters around them. And the microbiome, we're studying I'm not, but colleagues are studying the microbiome of what, and the corals have specific microorganism communities, and those change. Those microbiomes will shift according to environmental changes as well as the health status of the corals. So that's really a vast question. There's a huge amount of things that happen that both affect the coral and are recorded by the coral. I hope that helped. There's a lot of info.
Excellent. So you're saying there's not actually necessarily something as visible in the cores. You're looking more at the chemical analysis to give you sort of broader information.
Yeah, we can look at the cores, and like I said, growth rates are a really big noticeable thing when you have growth rates that suddenly go to a tiny year. And that's been used successfully to document the 1998 hurricane that clobbered Honduras, Hurricane Mitch. But I'm just trying to say that other things also cause great slowdowns in growth rates. So whereas the impact on the coral is quite clear, it's often difficult to back out either the climate information or the environmental information specifically from that. So,
gotcha.
Yeah.
So I think that answered the follow-up question. So I don't, not seeing any other questions in the chat box. I do encourage people to unmute themselves. But I also would encourage you, I know that Valerie sort of started us down this path, but do you have any ideas of, how you might discuss this topic or share this topic with the age group that you work with, ways that you might be able to share this with audience members and potential impacts you might see that it might have on them. So looking for ideas, you're all amazing educators, how you might use this in the education setting.
Or what would you need? Is there anything that would really, if I had this, then I could totally present this to my class. I'm just curious what that would be.
And please unmute yourself and share. We have a shy group today.
It's tricky for us because we've tried to do this, and I'll shut up as soon as somebody does anything. but in
Valerie
the
unmuted
meantime-
herself, so I'm going to cut you off, Konrad.
Do,
Something
do.
to say.
I'm just curious what data stands out in a coral reef core, coral, like what can students maybe see visually, and then what kinds of markers pop out the strongest that might be able to be used to answer a science question in a class?
Do you mean like a physical core looking at one?
Yeah, like that's what you're investigating, right? That's the data that you work with, is the core.
Yeah, but so there's so the data that I work with would be those chemical measurements, and so there's as many chemical measurements as there are chemicals, I suppose. The things that pop out, so when I was showing those records of temperature, and clearly the seasonal cycle pops out, and I think that when students see that, because it's not visible in the core is just a striped slab of rock. But then you start to show the data, and students realize that, oh, this is actually the summer and winter, every year going back in time. I think that's one of the first things that gets exciting. And then you start looking for, are there any weird, is there anything weird? Are there any missing years or any really big years? And we do find those. And then those stand out as well. To do that, of course, you need the data, but the data are available. It's not linear regressions, and it's really just looking at a data set and asking, what do you see, and trying to describe it. Because the other aspects tend to be mathematical, to really try and say, what do we see? Sometimes you don't see things until you do analyses, until you do a frequency time series analysis. There's things that you can do to pull those patterns out. You can say, a seasonal cycle is very easy. There's a seasonal cycle. It's quite strong. There could be decadal patterns. There could be these low frequency rises and falls. And those aren't clear. They're not like a seasonal cycle. They could be clear-ish. You can see them, but it can take mathematical techniques to extract those signals and really say, oh, here's the decadal pattern. Look at that. And that could even be done just with smoothing. But those are the kinds of things that you need to do. So it's not quite. This probably isn't helping, but it's not quite as easy as things that you can do with with the physical core, with the class. I'm assuming it would be trying to download data sets and then play with data sets.
Yeah, so if you're looking at the amount of calcium or barium, the minerals that are deposited, is that clearly seen a change in? I mean, I saw your data, so that's what you should be looking at, is the amount of deposition of these components.
Yeah. So any of the data sets that you would find online, some of them are things like strontium to calcium ratios. Some of them are this delta O18. It's an oxygen isotope. Both of those are very tightly coupled to temperature. And so if you take a data set from these archives, from the NOAA paleoclimate site, or from my site, the one that we've got, that we'll have in the as a part of this talk, I think Grace has that info that we put on the website. Then you'll get probably what you will get will be these chemical indicators through time or with depth. But either way, if you plot that and look at it, you're going to see, here's the seasonal cycle, here's the you'd be able to see these things we're talking about. You'd be able to see a seasonal cycle, the summer, winter, going back through time, and then you could start to look. It would depend on the coral, but you could find other things like lower frequency signals as well as annual signals, that kind of thing. And so they would be visible. For a lesson, it's hard to say. It would depend on, obviously, the kids and how how sophisticated they were and how far you could go with it.
Is there a particular type of coral you would suggest looking at?
Well, all of the ones that are in the paleoclimate archives are going to be, there's only a few different types that get analyzed a lot. The big ones that I was showing, they're all Porites, P-O-R-I-T-E-S. Porites lobata are the massive, 400-year, 500-600-year old corals. Yeah, so Porites would be what you'd look for, and that's predominantly what's going to be in the archive. If you're in the Atlantic, it'll be different. It'll be Siderastria. The Caribbean doesn't have Porites, which is unfortunate because that's the best coral by far to work with.
I think the interesting thing about what you do, Konrad, and to stress with the students as well, is that sometimes we think about taking cores, when we're talking about sediment, we might be looking for visual cues. And the really interesting thing about what you're sharing is that we're taking the cores, but then we're not like looking at them. We're actually, taking little pieces and doing chemical analyses, and that's what we're then plotting. And so I think that's a really nice concept for the students to get, that although we're not seeing visual cues, when we do a chemical analysis, we actually we can see trends. And to your point, I think one of the interesting things is always looking for what's weird, right? We see this long series. Well, where is there something weird happening? And then kind of asking the students, can we try to figure out what's happening? So I think there are a lot of really great questions that could be asked just around simply plotting that data set over time. So Valerie, I don't know if you wanted to follow up, or if anyone else wanted to follow up with ideas / questions. We have about 6 more minutes before we'll send you on to your next thing. So, and Carolina shared that there are a few Porites species in the Caribbean, just not as massive as the ones you were talking about.
Yeah, not lobata. Yeah.
Yeah.
Konrad, this is Ivar Bab from Yukon. Nice work, by the way. Really enjoyed your talk. Your work goes back to the late 18th century, so it includes, the Industrial Revolution and beyond. So there is a lot of natural variability, and that's obviously an important topic to understand. Are there any indicators, any signals from post-industrialization that you're able to tease out at all?
Oh, yes. Okay, so that's a great question. So I did make the case that my interest was sort of in the natural climate variability of the global system. So that's really, you make a very good point. That is predominantly going to be everything prior to the last 150 years. And so that is a part of what we do, is looking at the low frequency variability. But then really it's comparing what do the last 150 years look like compared to the 150 years or 200 years before that. These corals are only about 250 years old. Some of our longest records go back about 450 years. So we can start to look at that. And so you make it's a great question. So on the one hand, we often do see warming, good old regular global warming, or at least increasing temperatures, even though we're in tropical sites where temperature is kind of a secondary impact. It's not the primary climate signal, which would be really more about the rainfall. But so in addition to just temperature change, though, some of the things that we see, and this is why these data sets can be so rich in if you do data analysis and start looking at what are the frequencies of variability? Is there low frequency variability? And if so, how big is it? And what we find is that some of those anthropogenic signatures are changes in the frequencies of behavior. So we know that so many people study El Nino, and they use corals to build records of El Nino going back for as far back as we can. And one of the things that we do, El Nino has like a typical 3 to 7 year beat, a very, very fast beat. But that has changed. And we know that even over the 20th century, it went from being kind of fast to kind of very slow and weak to being very fast and strong again over the 20th century. And so that is, so many people are investigating whether those changes in frequency or power, changes in amplitude or changes in frequency of these oscillations, are those changing as a function of climate change, of anthropogenic emissions? The answer is almost for sure yes, and just the mechanisms, the dynamics get really complicated, but there are ways that warming induces changes in El Nino that can amplify, make the changes stronger, or more El Nino like, or more La Nina like. So those are some of the. It's a complicated question. It's a great question, and the answer is yes. These corals do have anthropogenic signals, and sometimes they're as simple as a bit of a warming trend on top of other changes, but sometimes it's really complicated, like changes in the frequency of variability of temperature or rainfall or windiness, all that kind of thing.
Excellent. And I see we're almost done. I'm going to throw a question out there. I'm just wondering, you're talking about taking samples from the corals. Is there any way, from living corals, is there any way to sample fossilized corals? Is there information that can be gotten out of those cores?
Yes, that's a great question. Very much so. And we do work with, if you think about it, everything underneath the living skin is a fossil already, even on a living coral. And so, one living coral here and one dead coral right next to it, we would call the dead one fossil when it might have died 2 years ago. And these two corals could be identical. But we do go after fossils that died a long time ago, 100 years ago, and then we get a deeper, older bit of record. The tricky part, you saw that we have to calibrate. We have to be able to take our signal and I showed you, like, here's a satellite record, and so we show our coral data next to the satellite data, come up with a relationship, and then use that relationship to extend the record down through the life of the coral. So the tricky part with a fossil is there's no top, so there's no satellite data to compare to. So, but there are tricks. You can try and overlap records. There can be the satellite record, and then here's the coral record, extends that farther back. And then here's a fossil coral that overlaps with the living coral. And we're playing those games. That's what you do with tree rings. Tree ring records are built piece by piece by piece by piece, nesting them one into the other, going back 12,000 years. We can't do that, but we are starting to nest records and get fossil records tied to the bottoms of living records to extend those records back up to 400 years. Yeah.
So I could see that being an interesting classroom activity too, where you have your students sort of nesting different data sets together. I've seen in middle school some lessons where they've done that, not necessarily with coral data. So I think that would be an interesting activity, but I sadly our time is up. So I just want to thank everyone for attending. Thank you so much, Konrad, for taking the time to share your expertise and your research with us. I know that I learned a lot. I want to encourage folks to ask questions on the, and I'm going to say it wrong, but WHOI for this session. If you think of something later, you have access to the recording for 6 months. Also want to remind you that there, I believe, is trivia coming up and then some networking. So the day is not over. So I encourage you to continue on with follow-up activities. But thanks so much for your time. Appreciate it. And have a great rest of your day.
Thank you, Konrad.
Thanks, everyone.